Okay, so you have $1,000. Who knows how you got this? You got $1,000, and you're gonna put it into a savings account, and your plan is to deposit $100 each month for 20 years. How much money will be in the account at the end of the 20 years? All right, well, let's start with the fact that we start with 1,000, right? We are definitely adding to it. Well, we are adding 100 each month for 20 years. Okay, so I put a ... to say we keep doing this month after month, year after year. So the question is, how many times are we adding this $100 into our account? Well, first, there are 12 months in each year. So how many, so let's go like this maybe. 12 months is to 1 year. Okay, as I have 10 of these. So this is happening 10 times. As 120 months is to 10 years. Okay, so 12 months is happening 10 times, but now it's actually 20 years, so it's double this, yes? So here we go with that, double that amount. So as 240 months is to 20 years. Okay, so here's what I just did. And I do think that there's a shorter way here. So I was thinking that, well, I know there are 12 months in each year. So for 10 of these, so 1 year 10 times is 12 10 times, so 120 months in 10 years. And then, well, there are 2 sets of 10 in each 20 years, so double that, and we should get how many months there are in 20 years. Okay, if we were writing this just as a straight multiplication problem, maybe we would write something like, there are 12 months in 1 year, and that happens 20 times because it's 20 years. So this happens for 20 years or 20 times in order to get 240 months. So we really could do 12 times 20 and end up with 240, and just think, okay, 12 months is happening 20 times, right? But I just kind of broke that 20 into first times 10 and then times 2, just because that's where my head went. So I just need you to know that sometimes you will have a strategy that maybe doesn't look exactly like somebody else's strategy, but as long as you are adhering to, using the operations correctly, you should be okay. Okay, so this $100 is being added 240 times. So really we are doing $1,000 plus $100 being added 240 times. All right. Handy calculator. Let's see. $1,000 plus $100 added 240 times. Ooh, $25,000. Okay, so how much money will be in the account at the end of 20 years? $25,000 will be in the account after 20 years. Nice. Fill in this table based on starting with 1,000 and depositing $100 each month. 1 month. Okay, so if 1 month has passed, then okay, so just so that we I'm going to put startup. We started with $1,000. After 1 month has passed, now all of a sudden we have $1,100 because we deposited $100. After 1 year, we've done that 12 times. Well, 12 100s is $1,200. Okay, so we actually added in this amount. So now we're actually at $2,200. So $2,200 because we've added in $1,200 and we started with $1,000. 5 years. Ooh, so I'm thinking of this like $1,000 plus 100 happening. Oh no, 5 years. So if 12 months happen, if there are 12 months in 1 year, that happens 5 times. Okay, 5 times 12, 60. Okay. I see here. So we're doing 1,000. And just to show where I got that too, the 60 came from me really doing. So for 5 years, I just did start with 1,000 and add to it $100. And this 60 came from me thinking of 12 times 5. Months and years. Okay. Just to actually lay it all out where all of these numbers came from. We started with $1,000 and we're adding $100 60 times. Okay. 1,000 plus $100 60 times. I get $7,000 after 5 years. After 10 years, okay, well, now if I look back to this, it's easy to modify because it's $1,000 for the startup, $100 per month and there are 12 months in each year. And now instead of 5 years, we are 10 years here. So, okay, I recognize a pattern happening. All right, for this one, boop. Let's do it. $1,000. So just so you know, I really am just banking on this thing right now. Whoops. What was it? $100. And there are 12 months in a year, and we are doing this for 10 years. 13 grand. Okay. And then we already know for 20 years. But again, this could have been rewritten as 12 times 20 right there. So that follows this pattern of $1,000 plus $100 times 12 for the months in a year times the number of years. Okay, 25,000. Got it. Okay, how much more would you have if you put away $125 instead of $100 each month? Okay. Super. Well, all I have to change in this right here is this 100 to a 125. So after 20 years, you would have, okay, here we go. I'm going to put it on my calculator, and then I'm actually going to show that on the page too. Okay, you would start with $1,000. And now you're adding $125 each month for 20 years. 31 grand. Okay. You would have $31,000. How much money would you have if you put away this instead of that? I think that's significant, actually. Nonetheless, so what we typed into the calculator here was, okay, we started with 1,000 and we added $125 per month, 12 times a month for 20 years. Just to show our calculation to get our $31,000. because I don't know about your teacher, but I definitely require all of my students to show their work. Because what if you write down something like $29,500 right here? Because maybe you, I don't know, who knows? Like maybe you made a mistake when you were typing it in here. For instance, what if you accidentally did this? And you got that, 30 grand. Where the only mistake I made was accidentally forgetting a zero when I was typing in 1,000. So I just want to know, I want you to know that it is very easy to make a silly mistake when you're typing something into your calculator. So showing this work, that allows me to know that you did understand the question and you picked the right strategy to solve the problem, but maybe you made like a typo or something, okay? So that allows me to actually give you credit for what your good mathematical ideas were, okay? So just FYI, it's always good to show what you were doing and how your strategy, or what strategy you picked to solve the problem. All right. Example 3, what is true? Put true or false for each statement. Multiplication always makes bigger. Okay, this is actually false. This is false because, get used to writing that out too. Because what if we did this? For instance, half of 100. Well, half of 100 is 50. So when we multiplied by a half, it did not make the values bigger. Now, if you have a whole number times a whole number, that will always be bigger. But, or what I mean by whole is something greater than 1 and another another factor greater than 1. However, fractions are kind of the breaker of this, that they always make something bigger. No, and what about times 0? I mean, for Pete's sake, there's 0. Not to mention negatives. Okay, let's look at number 2. 5 times 3, or 5 3 times, is 15. Is that equal to 3 times 5? Or, so here, this 5 3 times, this is 3 5 times, equal. True. Ooh, 5 divided by 3 and 3 divided by 5. Let's take a peek at that. 5 divided by 3. Ooh, la, la. 5 divided by 3. 3 divided by 5. Nope, not the same. Okay, so number 3, is this the same? No, that is false. I feel like I should write down every time we end up with a false statement in red, maybe. False. Okay, so 5 divided by 3 does not equal. So how many times does 3 go in? How many 3's are there in 5? It's not the same question as how many 5's are there in 3. Nope, definitely wrong. So another way, by the way, to see this as fractions, 5/3 is not the same amount as 3/5, for sure. 5 plus 3 is 8. 3 plus 5 is 8. Equals? True. Okay, how about this? 5 take away 3 is 2. 3 take away 5. Okay. That is definitely going to be negative, because you have the 3 to take away. So you take away 3, but then all of a sudden you still need to take away 2. So you have nothing left and you still need to take away 2 more. So this gets you -2. That statement is false. So let's see. Okay, 3 times 2 is 6, plus 3 times 4 is 12. That makes 18. And 3 times 8, I believe that's 24. So no. This statement is false. Okay, I wonder what the student was thinking. Hold on, I have to look at this. Oh, okay, so they were saying keep the 3 and 2 times 4 make it an 8. Nope, did not work out. Okay, so that, whatever that was, illegal procedure, just not mathematically sound. So let's look at this one where they modified. They're like, oh, if that didn't work out, what if this 2 and this 4 combines to give 6, I'm thinking, was the thought here. Okay, let's compute. 3 2 times is 6, plus 3 4 times is 12. That makes 18. 3 6 times is 18. That is truly equal. All right, so we did find some equality. Yay! It's always nice to have some equality there. Now let's look at a couple more and come back to all of these as a whole. So let's see. 2 5 times or 5 2 times, that's 10. And another 10 and another 10. That makes 30. And 3 times 2 times 5. All right, I'm just going to punch that in, and then 3 times 2 times 5. 30. True. Oh, I see, because this is 2 times 5 added 3 times. So this is kind of like viewing this as 2 times 5 being added 3 times. And then let's work this out. 18 times 3, I get 54. And 27 times 3, I think that's 81, yeah. And when I add those, so 54 plus 81, I get 135. Is that 45 times 3? 45 times 3, 135. That is true. Okay, so wait a minute. We've got an addition problem here. We've got a common 3 here. And it looks like maybe they did 18 plus 27 to come up with the 45. Huh. Okay. So, a couple of things that I would like to mention. When it comes to some of these, so let's look at 2, 3, 4, and 5. All of these had a rearrangement of order. 5 plus 3 became 3 plus 5. 5 divided by 3 became 3 divided by 5. These are all pinning down the commutative property. And that really the commutative property, we can do this for multiplication. We can say that 5 3 times, 5 added 3 times is equal to 3 added 5 times. This is just an orientation of the problem in my opinion. It works out for multiplication and it worked out for addition, but it did not work out for division and subtraction. So the commutative property holds for multiplication and division, or I'm sorry, multiplication and addition, but it does not work out for subtraction and division. And then when I look at the next few, here, let me stack these so that I can see them all at once. These all had to do with combining addition problems and rewriting them as pure multiplication problems. So when I think about 6, 7, 8, and 9, these are really talking about the relationship between multiplication and addition. And that we refer to as the distributive property. So when we're looking at something and we're rewriting this, we're really kind of distributing and combining. For instance, here, it looks like what they did behind the scenes is they treated this like, okay, so since rearranging the order works for multiplication, and we don't usually see the distributive property presented quite in the same way, I'm going to rewrite this problem as, okay, so 3 times 18 plus 3 times 27. And it looks like what they did is they viewed that as this had been a distribution of this original problem. So 3 18s and 3 27s, actually we could say this is 18 threes and 27 threes. So if we have 18 threes and 27 threes, then altogether we have 45 threes. Okay, so I just wanted to show you, or 3 added 45 times, that really these right here, but it looks like this was a misrepresentation of that because we really needed to say, okay, this was 2 3s and 4 3s making 6 3s. Okay, so I just wanted to make a shout out to the properties, you know, commutative working for multiplication and addition, but not division and subtraction. While the distributive property, even though we are taught that it always looks like this, the reality is you've been using the distributive property sometimes correctly, sometimes incorrectly, and when we rewrite problems and simplify them into one, that's what's happening with the distributive property. So I just wanted to, you know, bring that back into your attention because we are taught these words and these properties, but it's nice to revisit why they work and how they work and the relationship between multiplication and addition. Okay, let's write down some properties of real numbers. Okay, here we go. First, we said multiplication is repeated addition. This would also work with subtraction. Okay, so multiplication is used to represent repeated addition if we signed it like we did with the money, could also represent repeated subtraction. Spend, spend, spend. Okay, so slap a sign in it. And I would like to mention that because multiplication is represented as repeated addition, then every multiplication can be rewritten as an addition problem. Okay, so that means if we have something, maybe I'll save that comment for a minute. I just wanted to bring this back. So that's a property. Exponents are repeated. Okay, so just to bring this back into your mind, after looking at multiplication as repeated addition, I also want to remind you that exponents are repeated multiplication. Also, if they are signed, repeated division. Okay. We haven't really talked about exponents yet, but I figured if we were talking about multiplication as repeated addition or subtraction was signed, then we should, you know, remember too that exponents are used to represent repeated multiplication. Division. So, right, just so that we are crystal clear here. 3 added 2 times. And here, 3 times 3 is 3 squared. Okay, or 3 multiplied by 3. 3 multiplied by itself 2 times. Okay. Next, division can be rewritten as multiplication via the multiplicative inverse or the reciprocal. So, division as multiplication. And I'll include include this in case you've forgotten by the reciprocal or the multiplicative inverse. Okay. And what else? Oh, subtraction or takeaway can be rewritten as adding a debt. Okay, so subtraction can be rewritten as adding a negative. Okay. So let me just write a couple of examples of this. So division rewritten as multiplication, maybe you have, I don't know, 4 divided by, I'll keep it nice. 4 divided by 2, which is 2, we can rewrite this as 4 halves, which is also 2. Okay, I don't know why. It's like it sits there and I just want to actually complete it. That was a compulse for sure. Subtraction can be rewritten as adding a negative or adding its opposite. So I don't know, for fun, let's suppose we have 7 minus 4 plus 2. Well, this subtraction could be rewritten as, okay, so this is 7. You have 7, you take away 4, and then you add 2 to it. So one way we could say is you are adding a negative amount to that, or you're adding a takeaway, or you're adding a debt, however you want to view it. Okay. And just to make sure we're all on the same page, you have 7, you've got a debt of 4, that leaves you up by 3, and then you're up again by 2, so 5. Okay, and then the distributive property. I didn't mention the commutative property in here, but it's true that I use it and probably should have included it. But I wanted to say this about real numbers, and distributions can be handled in 2 ways. Okay, so for instance, making up a problem here, let's suppose we have 8 times 2 plus 7. Okay, you could either add and then multiply, so 8 by 9, add, then multiply. Or you could say that this is what? 8 2 times plus 8, 7 times, which would be what, 16 and 56. Okay, so you could have multiplied, then add. Okay, so bringing back the relationship between distributing and adding, or I'm sorry, multiplying and adding, we get back to that distributive property that we mentioned in that last example. Okay. Now, I want to mention this because already I've been using lots of different symbols for all the same operation. For instance, here I use this dot to indicate we were multiplying, and here I use these parentheses to indicate we were multiplying, and then here I use this symbol of a little tiny x to represent we are multiplying. This little tiny x goes away very quickly in college because we are going to use variables. And if we're going to use a letter to represent a quantity, then this little guy could definitely get confused with a regular x. So just to write down a few symbols for these different operations, immediately when I think of multiplication, I'm like, all right, Sometimes I represent 3 times 5 like that, not to be confused with 3.5 or 3.5. Sometimes so penmanship matters. Sometimes in order to make sure this doesn't happen, we write it with parentheses, 3 5s, or 5 3 times, or I'm sorry, 3 5 times. Sometimes I will represent it with a tiny x, probably not very common moving forward from here. And sometimes they are back to back. Now I'm going to write this with a variable like 3 apples, or let's suppose we have 5 apples, then this is 3 sets of 5 apples. Sometimes when you have a variable and it's back to back with a constant, this is actually multiplication. This is however many 3 times. So I wanted to jot that down too, even though that's like an expression more than just a pure written out quantities. And it'll happen to you. Division. When I think about division, the first symbology that comes to mind is this line with the 2 dots. So 35 divided by 7. Or we could rewrite the same division problem as 35 parted into 7 equal piles, or 7 equal portions. So that's a fraction view of division. And then, or we could look at it with this symbol, 35 with the division bar, 35 divided by 7, not to be confused with the square root symbol. So we have all of these different division symbols. Parentheses, okay. I write parentheses because there are a lot of symbols that indicate parentheses are happening. So here's what I mean. You could see in a problem parentheses explicitly written to bundle an operation together and say, do this. Okay, these go together. Or you could see brackets, and those are the same as these go together, do this. But here are some other kickers that are implied parentheses, but we don't write them down explicitly. Absolute values. We always do what's inside them first, but we just don't like to put absolute values right next to parentheses. And so we just assume that when you have absolute values, that you are going to treat them like, oopsie, special parentheses. Better get rid of that because I'm writing down a bunch of symbols. So absolute values are implied parentheses. Another set of implied parentheses is under an actual square root. Under a square root, we don't put the parentheses, but we really do mean everything living under the root is together. And then fractions. So fraction, numerator, and denominator. Okay, so there are implied parentheses around each numerator and each denominator. So I wanted to mention this because we kind of have gotten used to the fact that there are different symbols for multiplication and different symbols for division by the time we get here. But by the time we get here, sometimes these parentheses are really hard to keep track of because they're explicit, implied or implicit, implied or implicit, and implied or implicit. Okay, so there are some situations where we really do not see parentheses, but they are happening. Okay, let's look and take a peek at example 4 in the next video.